Well, thank you all for coming and this ungodly hour. When you become great physicists and organize conferences and school yourself, I recommend you start at 9:30. It's much better, but the organizers are really tough people for this conference, so 9 it is. All right, so I wanted to start by showing a few slides just for fun. Actually, most of these slides are stolen from papers on the internet. I'm embarrassed. I'm not thanking the authors. I will try to do a better job next time, but anyway, so be it. So that's an example of percolation, edge or bond percolation. On the square lattice, that's a sample exactly at p equals 1/2, where maybe I didn't say the obvious yesterday, that is at the percolation transition, there is an incipient infinite cluster going through the system. It can be shown that there's only one for an infinite system. It's a very important result. So here's the example of what typical clusters would look like at p equals 1/2. And of course, you may have small clusters like these little guys here. And then there's a big cluster. I was just trying to spot it. I think if I start here, go there, here, there, here, here, and there. I go from one side to the other. That's it. It's percolating, and your coffee is being made at the machine over there. We all know it takes time, but it works eventually. So that's a little example. Here are some examples of, okay, so here I'm managing to refer to the people who wrote a review. That's a review for mathematicians, 25 pages to define the Potts model, but you know, that's what mathematicians do. So I'm not saying there is much useful stuff in there, but it is interesting to use at least for all their simulations. So here are examples of loops in the loop model on the honeycomb lattice. That's the case where x is my k, so this is the case we call non-critical with small loops, and you see indeed small loops. This is the case critical where the loops are starting to get big. In fact, technically there is one infinite loop, but it may be a little hard to spot. And then this is the dense phase, the phase where x is greater than xc or k is greater than kc. Well, now we're having definitely several large loops. In this phase, there will be, in fact, an infinity of large loops. And like I said, they're fractal. So if you did the simulation on a very large lattice, took a little portion and blew it up, you would see something that quote unquote looks like what you had before, right? And here's an example illustrating the difference between n equals 1.4 and n equals 0.5. Of course, when n is smaller, there are fewer loops because it costs n to make a loop. So if n is very small, you tend not to have many loops. So you see there's a tension between n and k. If n is very large at fixed k, of course, you're going to favor having many small loops. If k is very large at small n, you're going to favor having one very large loop. So it's not so surprising that maybe there are some values of n where the physics is changing a bit. And in fact, for n greater than 2 and k real, the transition between the two phases occurs, but it's first order, like for the Potts model. That's why we restrict everywhere to n or k or q, sorry, n between -2 and 2. N being the fugacity of the loops. And remember, in the Potts model, we saw that what I called n, the fugacity of the loops, is square root of q. So if q belongs to 0, 4, n belongs only to 0, 2. Technically, it is only like half of the whole domain that we could explore. I'll get back to this a little later. One more cartoon. Yeah, I may have shown this yesterday, I forgot. Just to illustrate in a more elegant way the surrounding lattice of the square lattice. I drew this clumsily yesterday. Here is a nice cartoon. Here's an example of the duality, the relationship, between clusters on the square lattice and loops. So we're having the first lattice, which is the lattice of black dots. Only the bonds E prime in my notation of yesterday corresponding to the cluster expansion are shown. So here you see the bonds and you see the surrounding polygons. And in white are the lattices of the sides of the dual lattice, the thing I discussed in the question session. And the sides of the dual lattice, like we did, like I said yesterday, are connected by edges if and only if there is no edge crossing that given edge on the original lattice. So whenever I have no edge between two vertices on the original lattice, I draw an edge on the dual lattice, which here is drawn in dashed lines to make the picture rather legible. So you see that for a given configuration of black bonds, a cluster on the original set of clusters on the original lattice, there is a one-to-one correspondence with a set of clusters on the dual lattice. Black are clusters on the original lattice, and dotted dashed lines are clusters on the dual lattice. And the point is that, again, there's this one-to-one correspondence that allows us to establish duality because the polygon decomposition of the two lattices is exactly the same. All right, so this is also something easy. And finally, this is done with free boundary conditions. This is done with periodic boundary conditions. Soon I'm going to start worrying about boundary conditions. We'll see that it plays a crucial role. In particular, the equivalence between the loops and the clusters is not totally exact on a torus and homogeneous surfaces, which will mean really that the Potts model is not really, strictly speaking, a loop model. It is related with loop models, but as it stands, it's more like a cluster model, and we'll see what a real loop model is like very soon. Finally, last illustration. Again, I drew this in a very clumsy way yesterday. Here's a better cartoon where we're having the honeycomb lattice, and then its dual, which is the triangular lattice. And you see, for instance, that the loops on the honeycomb lattice are nothing but domain walls for Ising spins living on the triangular lattice. So there's relationship between the two lattices, which in the case of the square lattice becomes a relationship between the square lattice and itself. All this I said, but I think it's nice to illustrate it this way. And I also commented on yesterday already on the fractal dimension of the interior of loops, which are the clusters of spins at the critical point in the Ising model and in the high temperature phase. And you see they are diabolically close. This is 182 over 96, so they differ by 5 over 96. It's not much at the scale of the deficit of the US budget, for instance, but it's significant, of course, for a mathematician or a mathematical physicist. Okay, that's all clear? Very good. Bit sleepy, huh? I'm gonna wake you up with bad jokes, don't worry. All right, so let's carry on. Let's carry on, and I don't like the Potts model myself. I never understood it. It's because I never really understood the symmetric group. But pedagogically, it's very useful, and it helped us already give a reasonable meaning to these loop models, where the fugacity of loops is not equal to 1, but is some real parameter. So we're going to keep worrying about the Potts model, and our goal today is to move on in the direction of algebras before making the big jump into conformal field theory. So let us start by discussing something I'm sure you all know about, which are transfer matrices. So what we're going to do is we're going to think now of, again, a portion of a square lattice, And we're going to ask ourselves how to calculate the partition function in some sort of manageable way, for instance, by doing a simulation or analytically. So this is going to be the geometry I'm considering. I'm going to label the columns by label going from 1 to n, or the sites at a given horizontal row. And I'm going to try to calculate the sum of all the sigma i's running from 1 to q of the product over the neighbors of e to the k delta sigma j sigma k. So last time I did a high temperature expansion and I defined a model for every q. For now, I am keeping q integer. Yeah, so we wrote n star when I was a student. Now my mathematician friends tell me, no, n doesn't contain 0, or does it? Paul, what's the last fashion? Should I write n star? Okay, yeah. Then there's this. Anyway, q is not 0. All right, so how do you calculate this partition function? Well, the idea of the transfer matrix consists in performing this sum by using matrix products. So imagine, so first of all, let's think abstractly. Let's consider, let's write sigma, a configuration of, so I have to be a little bit careful with my notations. Here, I was a site of the lattice, so allow me now to call it Ri, because Ri is going to live in 2 dimensions. So this is a site of the original lattice, Rj, a site of the 2D lattice. And I should not confuse this label with the label I'm going to call I, which is simply going to be the label of the columns of edges running from 1 to n, right? So R denotes any point on the 2-dimensional lattice, while I itself denotes only a number that's running between 1 and n. So let's imagine that I give myself a configuration of n spins, say on the bottom row, and I introduce some abstract matrix, A sigma sigma prime. So this is a matrix that n by n, and it's got one element. Sorry, I'm gonna mix this up. It's matrix q to the n times q to the n, and it's a matrix, therefore, whose elements depend on the spins between 2 neighboring rows. So let's do an example with 3. 1, 2, 3. I'm going to have here sigma 1, sigma 2, sigma 3. And here sigma prime 1, sigma prime 2, sigma prime 3. And I imagine I have some matrix, therefore, that is q to the cube times q to the cube. And its elements are depending on the spins sigma 1, sigma 2, sigma 3, sigma prime 1, sigma prime 2, sigma prime 3. For instance, the first matrix element would be A 1, 1, 1, comma 1, 1, 1. It would be the matrix element associated with the choice sigma 1, sigma 2, sigma 3 is 1, 1, 1, and sigma prime 1, sigma prime 2, sigma prime 3 is 1, 1, 1. Okay, that's just one of the many matrix elements I can have. All the matrix elements are q to the cube, because I have q to the cube possibility for the first label and q to the cube for the second label, right? So that's an object I could introduce. And the point is, what is the point of worrying about this thing is that if I multiply sigma sigma prime with sigma, so if I multiply the matrices sigma sigma, AA, the matrix element of the product between sigma and sigma double prime by the rules of matrix products is the sum over all the sigma primes of A sigma sigma prime times A sigma prime sigma double prime. Okay, so in other words, if I have such a matrix, the matrix element obtained by multiplying the two corresponds to fixing the spins on the bottom row, fixing the spins on the top row, and sum over these. Okay. That clear? And I know that it's funny, the concept of transfer matrix is so utterly obvious when you've understood it and so mysterious when you haven't. So you're at the stage where some of you haven't. That's okay. So in words, the idea is to replace the calculation of the partition function by a product of matrices, using the fact that when you do a product of matrices, you do sum over spin configuration. So if you're smart enough, you may manage that to do things in such a way that a product of matrices will produce exactly the sum over all the spin configurations you are after. Indeed, let's now make this matrix a little more precise. So the choice of matrix we're going to make will be the following. We're going to decide that A sigma sigma prime, so remember A is a matrix Q to the n times Q to the n. So for a given sigma set of spins at the bottom and set of spins at the top, we're going to choose for the matrix element something very smart, which is exactly what we need from the partition function. So we're going to choose the product from I equals 1 to n of e to the k delta sigma I sigma j. And then we're going to take the product from I equals 1 to n of e to the k delta sigma I sigma prime I. In fact, we're going to be a little bit more vicious. We're going to decide that we have two coupling constants instead of one, just to keep track of what's going on. So we're going to say that the horizontal coupling constant is K1 and the vertical coupling constant is K2. So let's do things a little bit more generally like this. It's not a very mean modification. Instead of the product of a Rj Rk of e to the k delta sigma Rj sigma k Rk, what I have is e to the k1 whenever I have two neighbors along the horizontal axis, and e to the k2 whenever I have two neighbors along the vertical axis. So here it's going to be a k1, that's all these interactions, and here's going to be a k2, that's all these interactions. Okay? So this is my matrix element. And now the point you see is that when I multiply an A with another A, like I explained here, what am I going to get? Well, I'm going to get, for a given sigma, and sigma prime, I'm going to get, because of this choice, that the matrix element will be exactly the contribution to the Boltzmann weight coming from these edges. And then if I do A times A, the next A will count for me the contribution to the Boltzmann weights coming from all these edges and all these edges. And I'm summing over the intermediate spins. So if I repeat it, I'm building the whole lattice and I'm calculating the partition function by something which is pretty much the product over A matrices over the vertical axis. So if I have a system with n columns and m rows, I'm gonna have to calculate the product of A matrices. How many? Well, 1A here, 1A here, 1A here, 1A here, 1A here. So if I have m sites, I need m minus 1 A matrices, A to the m minus 1. So this is going to take into account the interactions from this horizontal and this vertical, this horizontal, this vertical, this horizontal, this vertical, all the way up to here, these horizontals, these verticals. Then I still need to take into account the interaction due to these horizontal bonds. So I need to multiply this by, I need a new matrix B. That matrix B will be just this. Sigma I plus 1, because it's I and I plus 1 which are neighbors, B. And then it depends what I want to do with the boundary conditions. So let's assume the boundary conditions are free, which means the spins at the bottom can be anything they want and the spin at the top can be anything they want. This means I have to multiply this by a matrix, a column matrix made out of ones, and then a row matrix at the other end made out of ones also. This is a number, and now the claim is that the number is exactly equal to the partition function for the system of n and m sizes. Yes. At last, a question. Yes, go for it. Sorry. Okay, go ahead. Your questions are tougher usually. So. How do we get what? How do we get all nearest neighbors couplings? Well, so again, this matrix takes into account all these couplings and all these couplings for a given row. And then I'm acting with the matrix m minus 1 times. So the first action of the matrix, the first A, takes into account all these couplings. Then I act with A again. So the next time I act with A, I take into account all these couplings, and so on and so forth. A to the m minus 1 takes into account all the couplings except the horizontal ones at the top, for which I need the matrix B. How would you get it? What do you mean? Well, that's one matrix element. Oh, I see what you mean. All right. Well, let's do an example. So sigma is a set of n spins. So let's go back to my example with 3 spins. So let's take for sigma. Okay, let's suppose the first spin is 1, the second spin is 2, and the third spin is 2. Okay? We take each values 1 to q. I take 1 to 2. And let's suppose sigma prime is, I don't know, 2, 2, 4. Let's take q large enough, so this is allowed. Okay? So that's one configuration of sigma, one configuration of sigma prime. What is the matrix element? Product from I equal 1 to n of a to the k1 delta sigma I plus 1. So that's sigma 1, sigma 2, sigma 3. That's okay. let me finish. Okay, I know, sorry, I mean, it's kind of dumb, right? But so that's delta sigma 1, sigma 2 plus delta sigma 2, sigma 3, e to the k2, delta sigma 1, sigma prime 1 plus theta plus delta sigma 3, sigma prime 3. So it's a horribly complicated way of writing that we have e to the k1 because of this bond, e to the k2 because of this bond. Okay, so that's one example of the matrix elements. So this matrix element gives me the Boltzmann weight corresponding to this choice of spin, this choice of spins, and then the algebraic construction puts together all the matrix elements into this simple object. Yes. Yeah, the B is for the top. Sorry? It's because the way I've defined A, I try to not introduce too many notations, but the way I've defined A, I put in it the horizontal bonds here and the vertical bonds. But what? So B is for the top, because the top does not have vertical bonds. Well, because of the matrix multiplication. So if I have, okay, let's finish with this example. When we calculated the matrix element A sigma sigma prime, we took into account these edges and these edges, but we did not take into account these edges up there. If I want to take them into account, I need to multiply by B. So what is the B matrix element? B, I see what you mean. That's what you meant? Okay, all right. Thank you, thank you. Yeah, it doesn't B, well, yes, okay. B is just diagonal. Yes, okay, sorry, thank you. All right, so if you wanted to put the system on the torus, you would need to take some trace and so on and so forth, but up to the decorations of the one on the left, the one on the right, the important point is that you can essentially calculate everything by powers of this matrix A. Okay, that now clear? I mean, everybody knows transfer matrices. I suppose I'm just wasting my energy stating the obvious, but okay. So, all right, so that's step number one. Step number two, we're going to write this matrix A in some slightly nicer way. So we're going to write the matrix A as follows. So first of all, I have my matrix B, which, yes, okay, so, let's more generally introduce B sigma sigma prime is product for I equals 1 to n of e to the k1 delta sigma I plus 1, product j equals 1 to n of delta sigma j sigma prime j. Let me write it like this, right? It's the same thing, but let me write it like this. So this is going to be B, and then let me consider, just for fun, C sigma sigma prime, which will be defined as the other term. So product for I equals 1 to n of e to the k2 delta sigma I sigma prime I. Okay, so I have that A is B times C. Uh, no, let me, first I act on the horizontal and then the vertical. So A is C times B, okay? Sorry for the notation. I should have done B and C, but that's the way it is. So A is C times B again, because first, the way I think of it, first I take into account the horizontal edges and then the vertical edges. So B is horizontal edges and C is the vertical edges. All right, very good. So now let's observe that we can write these matrices in a slightly more intelligent way. So B, I should have written 1 to n minus 1 because it's not periodic, it's open. The spins go from 1 to n. So let's now observe that we can write B as product from I equals 1 to n minus 1 of, and we're going to write it identity plus 1 over square root of q times e to the k1 minus 1 times some object I'm going to call e2i. And let's write C as product from I equals 1 to n of e to the k2 minus 1 plus square root of q e to I minus 1. Okay, so let's write it like this, and then let's try to figure out what the hell we are doing. All right, so B, what is B? B has a delta function between sigma and sigma prime. So the identity certainly is exactly what it is. So if I didn't have this term, the product of delta function I could write as just the product of the identities, each of them acting on the spin j. As for the first term, so what is the first term containing? The first term has an e to the k1 delta sigma r sigma I plus 1. So I should make sure that the matrix elements of E2i are such that when I do this composition, I get exactly e to the k1 delta sigma I plus 1 for each I. So I'm going to take E2i sigma sigma prime is square root of q delta sigma I plus 1 product from j equals 1 to n of delta sigma j sigma prime j. If I look at what I'm getting now, B sigma sigma prime, what do I get? Well, for each edge, first of all, I'm sending sigma to sigma prime, right? There's a product of j equal 1 to n of delta sigma sigma prime here, and 1 in the identity also. So for each edge, I'm just first sending all the spins to their identical values. But the point of this matrix is simply to ensure that for each I, whenever sigma I is equal to sigma I plus 1, the total contribution is 1 plus 1 over square root of q times square root of q. This is perverse, but it's because the e's will be nice object later on. I get 1 plus e to the k1 minus 1, which is e to the k1. So B sigma sigma prime is exactly equal to this. But what I've done is simply I have decomposed this product into a product of n minus 1 terms, and each of the terms, instead of writing its matrix element like this, I have encoded the matrix element into matrix elements of some object whose main feature is that it doesn't depend on K1. So I'm, if you wish, separating the dependency on the couplings and the dependency on the spins themselves. So that's the first object I needed. And then we can do the same for the second object. So the second object must now encode for us the matrix C. So C is very simple. It is just sending sigma to sigma prime. So sigma can be anything, sigma prime can be anything. And all I want is that whenever sigma I is equal to sigma prime I should have a coupling e to the sigma 2. So I need to have e 2i minus 1 equal, so let's see what we have in the structure. We have a e to the k2 minus 1 plus square root of q e to 2i minus 1 for each vertical edge, okay? So e to the k2 minus 1, I didn't write it, but it's multiplying the identity. So of course, whenever sigma is equal to sigma prime, I have to the e to the k2 minus 1. But then if sigma is not equal to sigma prime, I should have a 1, because if sigma is not equal to sigma prime, this thing should reduce to a 1. So e to the 2i minus 1 must allow for spin changes, so it should be something like 1 over square root of q product for j not equal to I of delta sigma j sigma prime j. So let's see the contribution of a given I in the product for C. For a given I in C, let's call it I0, I get e to the k2 minus 1 plus square root of q e to the 2i minus 1, which counts as what? E to the k2 minus 1, that's the identity, so it's at delta sigma I0 sigma prime I0 plus square root of q times 1 over square root of q product for j not equal to I0 of delta sigma j sigma prime j. Yeah, I'm not explaining this very well, I'm sorry. Let me do it again. Well, okay, I can write it like this, but let's write it a little bit differently. What is the matrix element of this between sigma and sigma prime? Okay. So for each I, this term corresponds to an identity. So for each I send sigma I to the same value, sigma prime I, and I have a contribution e to the 2k2 minus 1, except for I0, and for I0, I'm simply allowing the spin sigma I0 and the spin sigma prime I0 to be anything I want. There is no constraint with a matrix element of 1. So the sum of the two gives me an e to the k2 for each vertical bond, except for that one where I've allowed these two things to get detached, because I can have sigma I0 and sigma prime I0, anything I want for e to the 2 I0. So this is what I'm doing. I'm counting each vertical bond by propagating the spin exactly the same, and then these two I'm allowing to be detached. So the claim is C can be written that way. Sorry, I'm messing this up a little bit, but hopefully you'll understand it eventually. So we want to write B and C like this as products of two matrices. Each of them are themselves expressed locally. That's okay? Probably the best is to think of it yourself. I think, not that I'm lazy, but I know in this kind of game, it's like taxes. More explanations tend to kill explanations. think I'll stop here for this particular point. All right, so anyway, if you don't see it, just take it as a fact for the time being, and let's move on a little bit. Morally, again, it is rather simple. First of all, we calculate the partition function by encoding the sum over all spins into a product of matrices. And B, because the interactions are local, these matrices can be in turn built by product of very local little matrices, which are these objects, E2i and E2i minus 1, up to these extra decorations. And now it's very nice to think of this graphically. So think of it graphically. In fact, it's often a good way to make sure that what you're doing is correct. Again, what is E2i minus 1? Well, pretty much it is 1 over square root of q times an operation which takes all the spins sigmas onto the same spin sigma prime, which we can represent with an edge like this. This edge is not necessarily the same edge as what we've had before. Now I mean somehow that I identify the two spins. Maybe let me represent it as a wavy edge in order not to be confused. Except for the site I, which we do not force to be equal to the site, the spin sigma I, which we do not force to be equal to the spin sigma prime I. In fact, for each choice sigma prime I independently, I have a matrix element which is the same, right? So e to the 2i minus 1 simply propagates each spin to the same copy of it, except the ith one, which we allow to change into any other value, right? This is a good way to think of e2i minus 1. e2i is a little bit different. e2i, what does it do, e2i? Well, e2i, it sends every spin to the same copy, including the ith one, but on top it forces sigma I to be equal to sigma I plus 1. So this is this. Okay. So it's not a surprise when you think of it that you can write the partition function like this. For every edge, either the two spins on both sides of the edge are equal or they are different. And when you represent the matrices like this, you can imagine that when you take the product of all these B's and C's, you're going to represent all the possible configurations of the edges on the lattice. So this is a nice graphical representation of these two basic objects, e2i minus 1 and e2i. Very important to observe that if we have n pot spins, we have how many i's? Well, we have E1, etc., up to E. So let's see. For C, I get up to 2tn minus 1, and for B, up to 2e2n minus 2. So we go from E1 up to E2n minus 1. There are more E generators than there were spins. Yes? Sorry, repeat that from the beginning. For what? Sorry, for higher dimension? Oh. If we had next to nearest neighbors, that's your question. Yeah, good point. So this, as we will see in a minute, generates what's called a Temperley-Lieb algebra. And there is one algebra per Bayes diagram, really. So if you wanted to have second nearest neighbor couplings, for instance, what would we have? We would have to also take into account interactions between, for instance, 1 and 3, and so we could always represent this by adding an edge like this, right? So we would have a system like this, and you would need an other generator to represent this interaction. In general, whenever you have an edge, you need a generator. So it is a nice little result that if you take, you could actually think of this in 3 dimensions. So now in 3 dimensions, what would happen? If you imagine a Potts model in 3 dimensions, you will have slices of your 3-dimensional systems, which will now be pieces of the square lattice, and then you're going to propagate these slices. So you're going to have horizontal edges, vertical edges, and edges in the 3rd direction. For each of these edges, you could introduce such a matrix, and there would be an algebra related with that. So for any Bayes diagram, so to speak, there is a given algebra. It's very difficult to study in general, but it can be written down, and some properties can be explored. So yes, the short answer to the question is yes. If you have next to nearest neighbor interactions, you need more elements. And the question is very relevant when we think about loop models. The way we've defined loop models, really, we involve only nearest neighbor interactions. I will try to explain more why I'm saying this later. But if we allowed crossings, for instance, we would have to take into account next to nearest neighbor interactions. All this will become clearer, I hope, soon enough. All right, so let me carry on a little bit. What I want to do now is observe that these EIs, so the set, okay, so the associative algebra generated by the identity E1, etc., e to the 2n minus 1 will be called the Temple-Ellib algebra on but in order to fully specify the Temple-Ellib algebra, I need to see what kind of nice relations these EIs, E2Is obey. So let's look at this very quickly. First of all, the EIs are some sort of projectors. To see that, let's use our little graphical representation up there and see, for instance, what happens if we look at E2I minus 1 square. What happens if I look at E2I minus 1 square? Well, let me represent it graphically. This is 1 over Q times, and then what's happening is I'm propagating my spins except the ith one, except the ith one, sorry, propagating them once, that's E2I minus 1, and I'm acting again with E2I minus 1. So again, I'm going like this, like this, like this, okay? Okay, so that's what I'm getting. And then this spin is the same as this one, which is the spin of this one. So of course I can rewrite this 1 over Q times, well, this, that. And then what has happened here? This spin and this one, so this spin being what it is, this one can be anything, and this one can also be anything. So this is the same as this up to a factor Q. Again, because the spin in between can be anything I want. So that's therefore 1 times this diagram, which is square root of q e to the 2I minus 1. So e to the 2I minus 1 square is equal to square root of q e to the 2I minus 1. And let's now look at e2i. e2i square equal, well, let's do the same silly game again. So we get this, and then this. That's for one action. And then we act twice, so we need to draw something like this. And then what happens if we act here, where this is equal to this, which is equal to this, which is equal to this. But hey, we enforce that it's equal again, and we write something like this. Okay. So, and I square it, so that's square root of q squared, and this. So I have not changed anything. Really, e2i minus 1, all it does is, e2i, all it does is force I and I plus 1 to have the same color. If I act twice, I get just the same thing, of course. So that's square root of q e2i. Okay? So we're having our first relation, totally dumb relation, ei square is square root of q ei. Okay? We're having that, well, e2i act on the spin I and I plus 1. e2i minus 1 acts only on the spin I, so certainly ei and ej commute if I minus j is larger or equal to 2. So that's another nice relation. And now we're going to write the big, beautiful, important relation. Let us now consider the relationship that's worth a lot of money. So let's look at e2i minus 1, e2i, for instance. Okay, so the way I've thought of my system, I have, so to speak, propagated from the bottom to the top. So when I write a matrix product like this, with more than one element, what I mean is I first act with e2i, then with e2i minus 1, then with e2i, I act on the left, and I represent this diagrammatically by moving up vertically. So e2i, I have a square root of q, and then I'm acting vertically, so I'm having these diagrams. Okay, so that's the action of e2i. Then I want to act with e2i minus 1, so I have a 1 over square root of q. And then what do I do with e2i minus 1? Okay, I keep this guy, keep this guy, keep this guy, and now I must detach the first spin. So what this means, once again, is that this one is equal to this one, equal to this one, equal to this one, equal to this one. In other words, I have sent this guy to that guy, the same. These two have to be equal, but now this one is anything I want. And finally, I act with e2i again. So I multiply again by square root of q. And then I again have this, and then this one is equal to this one, equal to this one. So this is the product e2i minus 1, e2i minus 1. Okay, what have I gotten in the end? I've gotten in the end that I started with sigma 1, sigma 2, sigma 3, sigma I plus 1, etc. What do I obtain? I obtain the same sigma 1, the same sigma 2, the same sigma 3. Here I forced sigma I to be equal to sigma I plus 1. And in the end, what do I get? This spin is the same as that one. And because of this bridge here, this one is the same as that one, which is the same as that one, which is the same as that one. So in fact, these two are equal. So I can just as well conclude that this is square root of q times the diagram where I have this, because once again I force these two to be equal, and that's all I get. I could, if I wanted, put a vertical, a horizontal wavy line here, but I don't have to. This already tells me what happens. And this is therefore E2I. Exercise show that, yeah, I was told I have to give you exercises, by the way. I'll give you plenty of exercises. Ready? So exercise number 1, show that E2I minus 1, E2I, E2I minus 1 equal to E2I minus 1. Another exercise, by the way, you can play with Kirchhoff's theorem, count spanning trees. Imagine a nice graph where you can draw plenty of spanning trees and then count them using the discrete Laplacian. It's very healthy. So we have two small exercises. So what we have shown is that we have this amazing relation EI plus or minus 1 EI equals EI. Okay? So the algebra generated by E1 up to E2n minus 1 with the EIs obeying these relations is called a temporally algebra TLN of, so in general I'm going to write this as n, little n, hope it's not too confusing, TLN of big. It depends on n, the number of sides, and it depends on the parameter little n. Okay. For each diagram, so when I say base diagram, what do I mean? I mean that when I'm calculating the partition function, I'm starting with some set of spins and then I'm kind of propagating. So like I said, we could imagine calculating the partition function on many other structures. And the point is that the algebra will depend only on the base that we keep propagating through. So if, for instance, we had a periodic system instead of an open chain, we could similarly consider the partition function of the Potts model. Right? So it's a little bit hard to draw like this, but what I mean is simply that my system would live on a cylinder, while earlier what I had shown, we had a system living on a strip. If I lived on a cylinder, I would have an algebra with one more generator corresponding to the generator that closes the system. Let's call it E0. And there is a corresponding algebra. We'll talk a bit about it later. It's called the affine temporally algebra. More generally, like I said, if you had 3 dimensions, you would have an algebra associated with the plane, the square lattice, and so on and so forth. So there is an algebra per diagram. It's very rich mathematically, but let's not worry too much about it. What's important in this game is, I mean, the algebraic point of view is very useful, in particular to connect with conformal field theory. So conceptually, what we've achieved so far is not very much, but we've achieved the fact that we can write the partition function as a trace of matrices over matrices that belong to a certain algebra. And then the questions that will arise are, how about representations of this algebra? How about the relationship between this algebra and the, to be pedantic, the enveloping algebra of the Virasoro algebra in the continuum limit? And C, How about symmetries? We started by saying that the Potts model had a SQ symmetry, and now we're having some algebra. This algebra should be commuting with the SQ symmetry. Does it? What is the relationship between the symmetry and the commutant? Something that's become quite important in quantum information lately. So these are the kind of questions we're going to study next after the break. Yeah, I'm told I have to have a break. So let's have a break. Let's relax and see you in 5-10 minutes. All right. So I had a couple of questions at the break, which were very good. Mostly the question is, yeah, but you put square root of q somewhere in your definition. So what about if you had defined the e to I minus 1 differently? Well, yes. The point of the definition is we get the very simple algebra like this, with in particular no differences between the even and odd labels. If we had defined things any differently, there would be a difference between the even and the odd labels, and definitely wouldn't be very pleasant. Point number one. Point number two, at criticality, when k1 equals k2, actually, and e to the k minus 1 over square root of q is equal to 1, the way we've defined the algebra, the transfer matrix A is particularly simple because it's just a product like this with no coefficient left. So that's one of the reasons why do we define the algebra this way. Third of all, square root of q cannot be eliminated from the definition. I mean, it looks like you could renormalize EI to get rid of the square root of q and get real projectors, at least as long as q is not 0. But then the third relationship, of course, will be modified. It will have a square root of q. Right? So in the end, I promise the algebras for different q's are not isomorphic, even though as long as q is generic, in a certain sense, you could map them onto each other in some sort of algebraic equivalence, but definitely every q is a different algebra. Okay, so there are algebras of representations, something that maybe is not so easy to remember. We learn at school mostly about Lie algebras. We're all familiar with the fact that Lie algebras have representations. But Lie algebras are given in terms of commutators, and we know how to build representations of Lie algebras, starting from highest weight states and then applying some ladder operators and so on and so forth, right? Well, it so turns out that associative algebras also have representations, and they're a little bit more difficult to understand because we don't have these commutators. We don't have raising and lowering operators and so on, but nonetheless, they have representations just like the algebras. And I need to tell you a little bit about these. So first of all, this Temple-Ellib algebra is an example of what's called a diagram algebra. And you've seen it somewhat with my silly little cartoons. But there's a better way of thinking of the Temple-Ellib algebra as a diagram algebra. So I want to explain this now, and then we will see where it's coming from very soon. So let us introduce a set of 2n strings. So let me now forget about the edges in the Potts model. Let me just introduce diagrams with a bunch of strings. So here are 6 strings. that would correspond to 3 pot spins. And then let's observe that we can realize this algebra, the Temple-Elib algebra, by introducing very nice natural diagrams on this space of strings. The diagrams are defined simply by deciding that EI connects the string I and I plus 1. So in general, I will have a bunch of strings, and I'm going to have them propagate vertically, except that the ith and I plus 1 string are going to be connected like this. This is going to be what I will call EI. Okay? In contrast with the other definition I had with my pot spins, this definition doesn't see any difference between odd and even, right? I have never said that I was odd or I even. Point number 1. Point number 2, be very careful. Initially, I was a pot label used to label pot spins running from 1 to n. Now I is running from 1 to 2n, but that's the way it is. I'm not going to call it anything else. I would say, if you allow me a digression, as a theoretical physicist, notations are one of the most difficult things you have to face when you write papers, because you know pretty well what you're talking about, but if you really want to be rigorous and have the different notations for all the concepts, it is really a nightmare, even with all the tech packages. And so it's sometimes you just have to call things with the same name. Like K has meant very different things, I means different things. Well, that's the way it is. All right, so this is what we call EI. And now this algebra, the point is that these string diagrams give us a new representation of the algebra, as we can easily check, and that's really the nicest way to check all these relations. So for instance, let's look at EI square. EI square is, well, remember, we have decided to attach these two like this, so that's EI. What do we get if we do EI square? We do something like this, okay? So EI square is square root of QEI or NEI, simply means that we use isotopy. We say that topologically this is the same as the diagram for EI itself. And the little loop that we have obtained, we just remove it up to a factor n. Okay, so this is our rule. Loops are eliminated up to a factor n. Okay, so EI square is NEI. Very nice. How about EI plus 1 EI? Well, that's very simple to see. Now I act with EI, so I get this. Then I must act with EI plus 1. And then I must act with EI again. So this is EI plus 1 EI. And by isotopy, what I can do is just say, oh, okay, I can just pool these guys, and that's the same as, which is EI. Okay. So these diagrams, the action on these diagrams, provides a representation of the algebra. In fact, it is a faithful representation. That is, there's a one-to-one correspondence between the words you can form in the algebra and the diagram. So it is a very nice way to proceed. Now, these diagrams should remind you of something. What do they remind you of that we've seen earlier? The polygons, yes, of course. What we have done here is recover our equivalence between clusters and polygons, because these lines are just the polygons in the polygon decomposition. First of all, the counting is right. If I have my Potts model on the original square lattice, remember where the polygons were living? The polygons were living on the surrounding lattice, so I needed lines like this. For n Potts spins, I have 2n lines. And then what could happen to my polygons, remember? Well, when I had 2 lines coming, they could either get contracted like this, or they could go like this, which is exactly what I have in this representation. So going from the clusters to the polygons is like changing the representation of the algebra. So going from clusters to polygons is like changing the representation. And the trick to solve many of these models, so many of you know about integrability, I gather from my discussions. The trick about solving these models is that they may not be integrable strictly speaking, but you can use representation theory to solve them in the sense that you can find which irreducible representations of the temporal algebra constitute the Hilbert space. And then for each representation, you can find the spectrum of the transfer matrix by finding another representation in which you can use the beta ansatz. This is a very powerful trick that I'll explain maybe a little bit later. All right, now that's a lot of words. Let's start thinking a bit now about what we're going to call representations of this algebra. So unfortunately in physics, we tend to mix up horribly the concept of representation and the concept of module. That is, we identify somehow the space in which the EIs act with the representation per se, and the representation per se being the map between the generators and their matrix representation in the given space, right, in the module. So I'm going to keep doing this, but in principle, we should be a little bit more careful. All right, so obvious question to ask. Yeah, sure. Sorry? Yes, yeah, thanks, good point. Identity. Yes, that's right. All right, so many questions we could ask. Maybe the best, yeah, sorry. The model of loops, you mean? N, yes. Yes, if we have more loops, we have n per loop. N per loop, because this is what I mean when I mean going from clusters to polygons is like changing the representation. When we wrote the partition function of the Potts model as a sum of polygons as a loop model, we had square root of q per loop. We had n per loop. That's exactly what we're having here. Okay? All right, so where to start? Well, maybe the best place to start is to try to see what the action, how to represent the EIs in the diagram basis as matrices. So goal represent the EIs as matrices acting on diagrams. Let's draw a few examples of, actually maybe I could use my slides, it's going to be a little bit clearer. Let's draw examples of, can you all see that? Okay. Let's draw examples of words in this algebra. Let's have just very dumbly try to do this. This is the identity. Thank you for the identity. These three diagrams below, actually I have 9 diagrams below. What are they? This is E3, this is E2, this is E1. Okay, so let's start listing them. We have the identity. Now here we have E1, E2, E3. How about this one? How can I get a diagram like this? Well, let's start playing. How about a product E1, E2? What do I get when I get a product E1, E2? So I'm acting on 4 strings. E2 is this. E1 is this. So this diagram is in fact this one. So that's, which one is it? That's the one here. Okay, so this is E1, E2. In fact, all these I can express as words in the algebra. 9 of them. So if you start asking yourself, how many such words do I have? You have to observe that in the diagram on top, 4 lines are going through. In the diagrams in the middle, 2 lines are going through. So that's the subset of diagrams where 2 lines are going through. There's 9 of them. In the diagrams yet below, no lines are going through. So here I'm having a bunch of diagrams with 4 lines going through, 2 lines going through. How about the last diagrams? The last diagrams, well, this, for instance, is E1, E3. And I have more words like this. I should have written them all. I'm sorry, I was a little bit lazy. How about E2, E1, E3? So this is this. And then E2. Okay, so that's this one. And so on, right? So I have 4 diagrams with no line going through. The claim I'm going to make now is that on the left, each diagram on the left corresponds to a word in the algebra, and all the words in the algebra are represented by one of these diagrams. Indeed, when I give myself E1, E2, E3, I have 4 strings, E1, E2, E3, the natural first question to ask is, how many words can I form? I cannot form an infinity of words because I have my relations. So I have 1, E1, E2, E3. Then what can I do? Well, I can do E1, E2, I can do E1, E3, I can do E2, E3, okay? I can do, what else can I do? Well, I can do E1, E2, E3, I can do E2, E3, E1, I can do E3, E2, E1. and more. There's a certain number of words. I'm not going to write them all. Maybe that's an exercise I can leave for you. Exercise. Write all the words. But the claim is that in the end you would find 1 plus 9 plus 4 equals 14 words, that the total number of words that you can form with is 1, E2, E3. You understand that you cannot build arbitrarily large numbers of words because you have only 3 E's, and E1, E2, E1 is E1, E2, E3, E2 is E2, and so on and so on. So in the end you could fit only 14 words, and the claim is that these words are all represented here. Claim number 1. Yes? Sorry? Okay. So that's a very mean question. So in the periodic case, the algebra is infinite dimensional. Because in the periodic case, there are things that you cannot undo. So if we now wanted 4 strings again, but in the periodic case, we could now allow for this extra diagram, right? And now this is called E0. So if you have something like E0, E1, E2, E3, which, well, okay, let's not get into this too much, but there are words, there are infinity of words in periodic case. And you need some extra relations that are not in the algebra itself in order to decompose this word. So I'm kind of, I don't like getting into this because in particular the diagram algebra in the case of in the periodic case is really in a certain sense not faithful. So let's forget these diagrams. But the abstract periodic TL algebra, it is called the affine TL algebra. Actually, there are variants. Yeah, it's such a kind of world. Okay. The simplest is the periodic Temple-Elib, where you add just one more generator, E0, with the relationships that E0 square is square root of Q E0, and then so we had 2n minus 1, E0, E2n minus 1 equal E2n minus 1, right? You periodicize the relation. This algebra is infinite dimensional. We called it back many years ago the periodic Temple-Elib algebra. There are variants called the affine Temple-Elib algebra and so on, but in general the point is that it is infinite dimensional without extra relations. Now in physics, it turns out that the models we have do realize extra relations. So they are really quotients of the algebra. They don't explore the full infinite dimensional periodic algebra. But yes, this is good, would take us in many directions. But yeah, the short answer is that only periodicizing it makes it infinitely dimensional. It's a much harder problem, much harder. Okay, so let's not worry about periodic for now. I mean, I will talk about it later a little bit. But if you wish, the problem is really like in conformal field theory. The Virasoro algebra is really a beast. It's a monster. It's got an infinity of representations unless you add constraints. Constraints of unitarity, constraints of rationality, and so on and so forth. And it's really mapping onto the properties of the algebras that we are studying here. So the finite dimensionality of the Temple-Elib algebra in the open case is in fact really a little bit of an accident. I think for many models it would have been more natural to have an infinite dimensional algebra, and then we would have had to take quotients. But in the Temple-Elib case for open systems, it turns out to be finite dimensional. All right, so the claim number 1 to check is that write all the words and check their diagrammatic representation, okay? So that's the first thing to do. But of course, there are very smart ways to proceed, which consist in observing that these 9 diagrams can all be obtained by concatenating the diagrams on the right and their mirror images. So for instance, if I look at the second row, we have a diagram like this. And then if I take, say, this guy here and flip it, what do I get? I get something like this. Okay, so of course now I can just glue these guys. And what I want to do. Yeah, in this case I'm gonna. No, let's not do that. Am I making a mistake somewhere? Let's try again. This one, and then that one. Now I'm stymied. I want to reproduce these starting from these. What did I do wrong? Ah, no, I'm wrong. What did I do wrong? Sorry, help me. I'm just not seeing it right now. Yes. Thanks. So if I, so what confusing me was I was forgetting the top and the the mirror images, right? So if I take 2 of these diagrams on the right and draw not only them but also their mirror images. So once again, I take this one here and its mirror image, and then I take this one here and its mirror image. Thank you. If I do this, then I obtain one of the diagrams that I have on the left. Okay. So in fact, the number of diagrams on the left is always going to be the square of the number of diagrams on the right. Okay. The diagrams on the right themselves, they are something very natural when you think about looking at the action of these EIs in terms of diagrams. What are the diagrams on the left telling you? Well, they're telling you that. So what is a diagram like this representing? It is telling you that in the past, these 2 lines have come through without ever being connected. And these 2 were connected in the past. And when you think of it, this is the only information you need to calculate the action of the temporal ellipse elements, because what is the action of temporal ellipse? It is simply connecting diagrams and associating with each loop a weight square root of q. How can you know that you have a loop? You know you had a loop if and only if the two strings were connected in the past, because then when you close them, you produce a loop. If you close these two, you're not going to produce a loop because they were never connected in the past. But if you close those two, then you're going to get a square root of q. So the diagrams on the right form a basis. So the diagrams on the right form as a whole a basis on the right, form a basis for the representations of our algebra. Okay? Fine. Now, how about counting all the words? Well, let's now imagine acting on our basis with all the temporal ellipse generators. So our basis, we're having 1, 3, and 2. So let's represent it symbolically like this. 1, 3, and 2. Okay, just symbolic representation for the diagrams, right? And let's imagine we act with the EIs on these different diagrams, where we can, major result that's quite obvious is we cannot increase the number of lines that go through. So if I take the diagram on top, if I act on it with the identity, I get 1, which I'm just going to write as a 1 by 1 block. But I can also decrease the number of strings on the right if I act on this by E2, E1, or E3. That would be giving me diagrams that are down below. So things like this, things down here. Maybe I should not, well, okay, that's fine. So I have a 1 by 1 block, then I can get things here or things there. If I decrease the number of strings that are going through, if I act on the second type of diagram, I cannot increase the number of strings. So here I have a 0. But then different words in the algebra can either preserve the number of strings going through to be 2, or they can decrease it. So I can write things as blocks like this. For instance, if I act on the second diagram with E3, I preserve the number of strings going through, but if I act on the second diagram with, say, E2, I'm also preserving the number of strings going through, but sooner or later, if I act, say, with E1, E2, I'm going to decrease the number of strings. So the different elements of the algebra act on the three diagrams in the middle row by either conserving the number of strings or decreasing the number of strings. And finally, if I act on the diagrams with no string going through, certainly I have a 0 here, I have a 0 there, and then I may have some non-trivial action here. So the action of the different words in the algebra, any word in the algebra, is bound to have an action that he will have his matrix form. It will always decrease the number of through strings. It may keep it or it may decrease it, but every word in the algebra has this kind of shape when I represent it as a matrix acting on the words. And I can, once again, perfectly well represent it as a matrix. For instance, again, E3 acting on the first diagram of the second row is just equal to, as a matrix element, which is square root of q. Okay, so in general, every word in the algebra will have this kind of representation. Okay. Now the point is, each of the diagonal part provides an irreducible representation of the algebra. For instance, if I look at the action on the diagrams with 4 strings, what kind of representation do I get? Well, the identity on 4 strings acts as the identity. Otherwise, every EI diminishes the number of row strings. So if I restrict to the diagonal action, every I is just equal to 0. The only element of the algebra I have in the identity. So in this space, all EIs are 0, and the representation I get has only the identity. It is a trivial representation where all the EIs are 0, they satisfy EI squared is square root of QEI, and so on and so forth, but they are otherwise trivial. We can look at the action of the generators, for instance, in the second space now. Let's look at the representation we get on the second space. The second space, I have 3 diagrams. Let's look at the action we get. E1 acting on the first diagram, which I'm going to represent as a bra, is 0 in the restricted to the second space, right? Because E1 acting on this diagram diminishes the number of through strings. It is something like this. So this is fine, but if I restrict to the action in the space generated by these 3 vectors, if I forget this part of the action, then E1 is 0 on this space, on this state. What is E1 on the second state? I have this, and then I connect like this. So E1 acting on this state is equal to this guy. And finally, E1 acting on the last one, is equal to equals square root of Q. So E1 acting in this space, this matrix, for the particular case of E1, any word has this structure, but this matrix for the particular case of E1 has action 0, 0, 0. The second element is sent to the third with a 1, and the third element is sent to itself with a square root of Q. Okay, so unless I made mistake, this is the action of E1 in this space, and then it could also give states down below, but I want to restrict to this. So for each word in the algebra, I can, in each subspace, write a certain matrix, hang on, and the point is that these matrices give me an irreducible representation of the algebra. Yes? Yeah, I set it to 0 in this space. Yes. Okay, I factored out by this. Yes, it is, I should say, send it to 0. Okay, I'm taking only the quotient. Okay, so these definitely form representations of the algebra. The claim that they are irreducible would have to be shown, but I'm just claiming it's true. It is kind of easy to show in practice. What does it mean that it's irreducible? By the way, it means you cannot decompose the space into a sum of 2 spaces, each of which would carry a representation of the algebra by itself, right? So this is what we have done here. We have already done this decomposition. So what's left is an irreducible representation. For generic Q, yes. In fact, yeah, let's say it's generic Q. Yeah. If the algebra happened to be, if we were having special values of Q, things would be a little bit different. I'm just talking about generic Q here. In particular, if Q were equal to 0, for instance, you can easily check that other things could happen. Yes. Sorry? The second line with the 0? Yes. Yes. Because I'm only looking at the action of E1, the reduced action on the space generated by the free states. I'm not wondering about these things here. So, if you wish, I'm projecting everything onto the space generated by the free states in the middle. Okay. All right. So the claim again is that each of these produces an irreducible representation. So in general, what you're going to have is that you're going to have if you have two n strings, how many representations are you going to have? Well, the representations are labeled by the number of through strings. The representations Wj are labeled by the number of, so it's called through strings or straight strings or something. Defects sometimes, I'll call them through strings, by the number of through strings, which is 2j. So here on the cartoon, on the screen, I have W2, W1, and W0. Okay, and it can be shown that the dimension of Wj is equal to the difference of binomial coefficients, which here it is. Okay, so I am traumatized of the binomial coefficients. I never know which number to put on top and which number to put on the bottom. So if you use to the other convention, that's fine. You just know what the largest one is and the smallest one is. Okay, so this is the dimension of Wj. Let's check it in our example. Here we have n equals to 2, 2n is equal to 4. So I call these numbers often dj. So d2, what is d2? d2 is obtained by 4, 4, which is 1. d1 is 4, 3 minus 1, which is 4 minus 1, which is 3. And d2 is 4, 2 minus 4, 3. 4, 2 is 4 times 3 over 2, that's 6. So that's 6 minus 4 equals to 2. Okay, so we get 1, 3, 2, which are exactly the dimensions we have. In general, it is not too difficult to show this formula by counting what? The number of ways you can pair points without producing crossings, right? That's what these numbers are. So that's point number 1. Point number 2, once you have the representations, the dimensions of each representations, it is also easy to find the dimension of the algebra. The dimension of the algebra is given by the sum from j equals 0 to n of dj square. Why? Because the dimension of the algebra is the number of independent words you can build, and the number of independent words you can build is in one-to-one correspondence with all the matrices you can obtain in each of these blocks I have on the diagonal, so that the sum of dj square, which you see here on this cartoon, because once again, once you have an element of the basis and another element of the basis, you can always stack them on top of each other and form a word in the algebra. So the claim is that this is the dimension of the algebra, and the result is a very famous number called the Catalan number, which is the binomial coefficient. Sorry. Well, okay, let's write it like this. 1 over n plus 1 to n. For instance, for n equals 4, sorry, n equals 2, we get 1/3 times for 2. Yeah. So that's 1 over 5, 8, 4. So that's 8 times 7 times 6 times 5 over 5 times 4 times 6. So the 6 vanish, the 5 vanish, and I get 14, which is 1 plus 9 plus 4. Okay. You could define the algebra on an odd number of strings as well, so that's why there was a small misprint between 2n's and n. This is, in this case, the algebra on 2n sides, right? 2n. So that's the dimension of the algebra. And I'm claiming these without proving any of these results, but again, they're not particularly difficult to prove if you are into a little bit of combinatorics. Let me just add 2 words and then I'll be done with it. These numbers should strike you as very natural numbers. You've seen these numbers. You have seen these numbers before. If you were to think of a tensor product of spins 1/2, so now change of topic, seemingly, take a tensor product of 2n spins 1/2 and ask yourself, how many representations of spin j will you get in this tensor product? Question? What is the number of representations of spin j? Well, it's easy to find the answer to this question. How do you do this? First of all, you count the number of states with Sz equal to j. Let's do that. How do we find Sz equals j? Well, we have 2n spins 1/2, and we start with 2n spins all plus, and we flip m of them. Flip m of them. So if I do this, I obtain a spin Sz, which is n spins 1/2 initially all plus, that's Sz equals n, and I flip m of them. If I flip m of them, I replace a spin plus 1/2 by a spin minus 1/2. Okay? So Sz is n minus m. So if I want Sg equals J, I need M is N plus J. Okay. So how many states with spin J do I have in my system? I need to flip M of them, and I have to choose this M among 2n spins. So the number of states with Sz equal J so the number of states with Sz equals J is the binomial 2n n plus J. But a state with Sz equals J is not necessarily a highest weight state. How am I going to count the number of representations of spin J? I need to find the states that have an Sz equals J and that are not the S minus of something else. How can I count the number of S minuses of something else? Well, what I can do is take all the states of spin J plus 1. If I have a state of spin J plus 1, by construction of representations of SU2, I can always act and lower it by 1. So the number of states with Sz equals J plus 1 is 2n n plus J plus 1. And therefore, if I subtract the two, the number of highest weight states of spin J is equal to 2n n plus J minus 2n n plus J plus 1, which is exactly the same as this. So, of course, this is not an accident. We will see next time that in the particular case where Q is equal to 4 or n is equal to 2, the Temple-Elib algebra is nothing else but group algebra of the symmetric group acting on the tensor product of spins a half. And in that case, of course, this is in one-to-one correspondence with the centralizer of SU2 in the tensor product of spins a half. And that, of course, is the dimensions of the algebra. And we will also see that these diagrams are nothing else in that case but singlets in quantum spin chains. So all this and more, like they say, next time. Thank you. Okay, sorry, I went over the time. No time for questions. Yeah. No time for questions. No time for questions. Okay, sorry. And I'm embarrassed for the next speaker. So we can have the question right now in 5 seconds. Please come.